Hey there, class. Welcome back to the next lecture in the acid-base series. And this evening we are going to be going over acid and base strength. I am breaking this into two parts. So if you go in the OpenStax book to chapter 14, specifically 14.3, section 14.3, it is very long and detailed. So I want to break this apart into two parts just because if I tried to put it all into one, it's going to make for a very long video, probably close to an hour, if not longer, with worked examples. So I feel it's better to break these into two sections. So you will see a part 2 to this that will be uploaded. But keep in mind that these both go together for section 14.3, which is certainly the longest section in chapter 14 dealing with acid-base equilibrium, which really deals with acid and base strength. So we're going to start this portion off by talking about how can we define acid strength. So in the last lecture, we were talking about pH, and pH is an indicator of relative acid strength. So when we measure pH, we're measuring the free hydronium or hydrogen ions that are in solution, which is by definition what makes a compound acidic, or it's the acidic property of a compound. So pH is a direct measurement of acid strength. However, there is a better measurement, which is we're going to start taking a look at the equilibrium constant. And I don't even necessarily want to say better, but it's a more specific measurement, whereas the pH scale has certain limits to it. Okay, so when we start getting into Ka and then later pKa, that's going to open up a wider ranking scale and give some more precision and specificity to how we define acid strength or acid weakness relative to that. So the way that we can describe acid strength in words, going back to a Chem 111 or a Gen Chem 1 view, is that the strength of an acid is going to be how readily it will dissociate into the hydronium ion or the acidic protons. And most of these examples we're going to be talking about hydronium ions just because we're in water. So whenever you have H plus sitting around in water, the water picks it up to make it H3O plus, which we call the hydronium ion. Okay, so the more readily the acid will dissociate or give off those hydronium ions, then the more acidic the acid is going to be. So this is something that's usually covered in General Chemistry 1, but we're just going to mention it here. This is taken directly from your textbook. So there are 6 strong acids and 6 strong bases. This is not necessarily a comprehensive list. There are other strong acids and bases, but these are the most common. And when we look at these typically are the ones that are going to be ranked as 100% dissociation, meaning if we dissociate 100%, these are the strongest of the strong. All right. So perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic, nitric, and sulfuric. Those are by far the top 6 and the most commonly used ones that you'll hear about. And then you can see there's a lot of the different hydroxides over on the right. Specifically, those top 3 are known a little bit better than the other 3 as far as industry and their use, especially sodium hydroxide and potassium hydroxide. Those 2 are very common in most labs. Okay, but the point being these are all strong acids and bases because when you put them into water, they will 100% dissociate into either their hydronium or hydroxide respective ions. Okay, so let's start tying this into equilibrium. We have a general definition about acid dissociation, but what about equilibrium in the actual math and concentration? So let's tie that in. So since the strength of an acid is going to be determined by its ability to create the acidic protons, then we can directly observe the strength of that acid through its equilibrium constant, which we are going to call Ka. So K being the equilibrium constant letter, and then sub A is going to simply represent for an acidic solution. Okay, so we're going to start branching off. Chapter 13 was general equilibrium. So we had Kc, which was basically just representing a catch-all for any type of concentration. But in reality, when we start going through this, we're going to look at acid bases, we're going to look at solubility, which will be called Ksp, bases will be Kb, acids will be Ka, we've seen water, which is Kw. So essentially anything that can be in equilibrium, we can create an equilibrium constant for. And these little subunits are just sort of giving a little more definition as to what type of reaction we're looking at in equilibrium. All right, so take a look at this here. If it's the products over the reactants, right? When we're looking at this, we've got hydronium ions that are going to be created as a product along with some sort of conjugate base. And then we have HA representing the acid. So if we take a look here, okay, one of the other ways that we can define this is by percent ionization. So when you have a strong acid, we know that they go 100%. So you'd have 100% ionization, all right? But for weak acids, this is a very useful tool in order to sort of judge one acid against another, meaning how much of it is actually going to dissociate and create the acidic content in solution. All right, so we express this as percent ionization, and percent ionization can be set equal to the acidic content at equilibrium over the initial concentration of the acid solution. And you times that by 100 because this is a percent. So that would normally give you some sort of a decimal or a fraction, and then you would times it by 100. All right. Now, again, with the idea of a weak acid means that not everything is going to dissociate compared to the strongs. So if the acidic content is found at the top, and the initial acid is found at the bottom, we're not expecting the hydronium ion content at equilibrium to be larger than HA. Okay, so I just want to point that out here. This fraction should always be less than 1, or if it is 1, we're talking about one of those very strong acids that we mentioned a few minutes ago. All right, so we're talking about Ka here, but Ka is not the only thing. There's also Kb, as we've mentioned. And Kb looks a little bit different. So instead of Ha plus H2O going to the hydronium ion and the conjugate base, we now have the base becoming a conjugate acid, which we call Hb, and it releases hydroxide, right? So in the same sense that an acid generates H+, a base generates the OH-, okay? And we can calculate that as Kb. And with Kb, we can say that we're looking at the content of the conjugate acid times the hydroxide content, and we divide that over the initial the equilibrium concentration of the base, right? So there's a useful tool that we can utilize drawing back on to Kw. And as you'll notice, as we go along here, we continuously reference Kw. So it came up in the first lesson, then with pH and POH, we referenced back to it, and now here it is again, and we're talking about Kw. So Kw is a very important value that we need to be keeping in mind during these lessons, okay? If you know the Ka of a given acid, you can find the Kb of its conjugate base. So remember, in the first lesson we talked about conjugates, acid-base conjugates. Okay, so all you have to do is set the product of both equal to Kw. Okay, so if you take a look at this, you have Ka times Kb, and we can set Ka equal to the hydronium ion plus the conjugate base over the acid. And then for Kb, we can refer to that as the conjugate acid and the hydroxide over the base. So since we're talking about the same acid-base pair, if it's a conjugate, they're just labeling HA as the conjugate acid because it would be the conjugate acid for the base here. So HA drops out with HA, and the A- drops out with the A-, and we see that H3O plus times the concentration of hydroxide is equal to Kw. And that, again, is Ka times Kb. So if you know one of these, Ka or Kb, you can find the other for the conjugate, okay, if this is an acid-base pair. So this is a very useful tool, and we're going to go over now and practice some calculations in order to see how some of these equations work. Okay, so here are the acid-base calculations. I've got a couple that are percent ionization, and then a couple that involve Ka and Kb. And we'll obviously practice more of these throughout the summer semester as we continue in class. So the first question says, a 0.125 molarity solution of nitrous acid has a pH of 2.09. What is the percent ionization? So the first thing that we're going to want here is the actual equation. So nitrous acid is HNO2. It would be aqueous. And it's going to be in water, as all of these reactions during this semester are. And we can set that equal to its conjugate, NO2 minus. That would be an aqueous ion. Plus, we'd have H3O plus, okay, aqueous. So if we take a look here, this would be considered an acid. This would be considered a conjugate base, right? And this, in this case, would be considered base. And the hydronium would be considered the acidic content, the conjugate acid. All right, so now, here's the key, all right? Percent ionization, we need to find that H3O plus concentration at equilibrium. So what it did give us, while it didn't give us the direct concentration, it did give us the pH, and we can work with that. So if we know the pH of the solution, it's telling us information about this right here, right? Because pH is equal to the negative log of the hydronium ion. So in order to undo that, we're going to take the negative log, and that's going to be 10, I should say the anti-log, not the negative log, okay, 10 to the minus 2.09. So if you're confused as to what we're doing here, go back and look at the previous lecture that we had on pH and POH. All right, now also remember with significant figures, because the pH is 2.09, this is that placeholder digit, so we're really going to end up with 2 significant figures instead of 3. And so the answer here should be 8.1 times 10 to the minus third molarity. Now that is the concentration of the H3O plus, but that is not the percent ionization. So now we need to set percent ionization, which we'll abbreviate as percent ion, equal to the concentration of the H3O plus, which we just determined was 8.1 times 10 to the negative third. And that goes over the initial concentration of the acid, which is 0.125 molarity. So we're going to say 0.125 molarity, right? And we can multiply this by 100 and get our final answer. So if you put all of that into your calculator, you should end up with 6.5, and that's where we cut it off for sig figs because only 2 sig figs up here. 6.5%. Okay, so the nitrous acid with these conditions right here would ionize about 6.5% into the product form. So that would make it a fairly weak acid compared to acids that push almost 100% to the product side where it's all hydronium ion. Okay, so again, this is a good technique for comparison purposes. If I have 2 or 3 different acids and I want to judge their strength and or weakness, I can take a look at the percent ionizations for each and judge them against one another. And obviously the one with the highest percent ionization is going to be the strongest of the batch because that one is pushing out the most amount of acid content. All right, now to piggyback off of this, we've got the Kb for NO2 minus is 2.17 times 10 to the negative 11th. What is the Ka of nitrous acid? So we're still using this equation that you can see up from the first question. All right. In order to solve this, we're going to need to take advantage of the Ka, Kb, Kw relationship. So in order to do that, now I'm going to rewrite the equation down here for the sake of what we're working with, just so we can make a clean run at this problem. So this would be aqueous, plus we had water as liquid, right? Goes over to the ion in equilibrium, NO2 minus, aqueous, plus, and keep in mind, this is part of why you want to know your nomenclature. When it says nitrous acid or something like that, you need to know what it's talking about and be able to pull out the correct substance. So, in this case, what are we looking for? Well, the Kb is given, right? It's telling us the Kb of this base right here. Now, if we know the Kb, this is what we were talking about on that slide where Ka and Kb are going to give us Kw. we can find the Ka of this because it's a direct conjugate pair by setting this equal to Kw. So what we know is that Kw is equal to Ka times Kb. Right? So algebraically rearranging this, I can take Kb off one side, bring it over to the other, and I end up with an equation where Kw over Kb is equal to Ka. And this is what I could use in order to solve this. So let's go ahead and do that then. All right. So what I would do is I'd say Kw, which we can represent as 1.0 times 10 to the negative 14th, over 2.17 times 10 to the negative 11th, right? So it's Kw over Kb. I can set that equal to Ka, and if you put that into your calculator, you should get 4.6 times 10 to the negative 4th, and that is the Ka of the nitrous acid. And that's the answer. All right, so hopefully you guys are feeling comfortable with this. This is nothing more than working with different equilibrium constants. So while there's some new techniques, there's Kw, we really haven't moved that far away from equilibrium at this point. And it's going to come back because in part 2, or lecture 2, we're going to start seeing the ice charts pop back up. All right, so here's the next question. A 0.10 molarity acetic acid solution has a pH of 2.89. What is the percent ionization? So again, you're going to need to know what you're working with here. So one of the things that you need to know for the course is the acetate ion, which carries a -1 charge. Acetic acid is simply the protonated version of that base. So in order to draw this out, we would say I've got CH3, CO2H. Okay, that's going to be aqueous. That is the acetic acid. And because it's aqueous, we're dealing with water. And keep in mind, anytime we do Ka, Kb, water is always dropping out. So remember, back from the previous chapter, the solids and the liquids do not participate in the equilibrium constants when we're working with this. Right, so acetate ion minus aqueous plus the actual acidic content that's coming with this. So this is going to be very similar. In fact, it's going to be identical in terms of the math to the first problem we just did. Right, so we know the pH here. The pH of this is 2.89. So what I need to do is do antilog 10 to the negative 2.89. And if you do that, you should get 1.3 times 10 to the negative 3. All right, now, this is the concentration of the H3O+. So percent ionization is going to be the concentration of the H3O plus over the initial concentration of the acid, which was 0.10 molarity, times 100. Okay, and this is going to equal 1.3%. Right? So 1.3%, if that's the percent ionization for the nitrous acid, for the acetic acid, if we want to compare it to the nitrous acid is sitting at 6.5% in that previous example versus the 1.3%. So we could rank or start ranking these acids, and we could say the acetic acid, at least at this concentration, is going to be weaker than that of the nitrous acid. All right, now, here's the last problem. Okay, again, using this equation up here. So I'm going to start writing that out. Okay, vinegar has an equilibrium concentration of 0.0787 molarity acetic acid, and it's got 0.00118 molarity for both the hydronium and the acetate ion. The acetate ion is that conjugate base. Okay, so what is the Ka of acetic acid? All right, well, let's redraw the equation here. So we've got acetic acid aqueous plus water in equilibrium with the acetate ion aqueous plus the hydronium. All right, so when we do this, what we're now going to be looking for is almost like the classic sense. There's no Kb involved in this calculation. We want to set up an equilibrium constant. It's giving us the concentrations at equilibrium for the vinegar, right? So what we would do here is do a classic example just like we did in chapter 13, where we can say the Ka here is going to be equal to the concentration of the H3O+, that was given, times the concentration of the acetate ion, that was given, right, over the acetic acid concentration. Now, keep in mind, these examples have been 1-to-1 in their ratios. Just remember, if you have stoichiometric values that are greater than 1 when you're balancing the equation, you need to raise these concentrations to that power. Okay, so if we go back up and we look at the problem, it was 0.00118, and that is the molarity for these top two right here. So what I'm going to do to simplify this is I'm just going to square that value, because it's saying that it's that concentration for this as well as this. So we're taking the same value times itself, right? So this is going to be 0.00118, and that would be squared. Okay, and then that would be over 0.0787. And that is the molarity of the actual acetic acid itself. So if you put that into your calculator and you solve that, you should end up with 1.77 times 10 to the negative fifth. Okay? And that would be the Ka for the acetic acid. Now, when we start doing this, in the next lecture, we're going to start taking a look at some of the weak acids where we have an initial amount and then we want to solve for the concentrations at equilibrium. That is when you use the ice charts. So some people, you got to pay attention to the wording. It says vinegar has an equilibrium concentration. That means they're giving the concentrations at equilibrium here. We don't need to do ice if we already have those equilibrium concentrations. Ice is used when we want to either find initial and we have equilibrium, or we want to find equilibrium and we have initial. Okay, but just to calculate the Ka, if you're handed these, it's just the plug and chug type of method. So anyway, that is going to wrap this up, and we will move on to section 2 of this acid-base strength and continuing to look at Kas and Kbs in the next lecture. So this is probably where we're going to pick up the course when we get ready for our next review, and then next week will start posting some of the content that deals with the more complicated ice solving of these, and then we'll continue forward. We're going to take a look at some things like buffer solutions and salts that become very important in the lab when we move through the rest of the chapter here. So this is a larger chapter. That's why it's set aside for 2 weeks instead of 1 week, but this should be pretty good for the content this week. So I hope everybody was able to follow along. As always, reach out to me if you have any questions. Thanks for the attention, and I will see everybody for the next lecture.